In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos. Each note, a shot of pure ether, struck the Einsteinian demons, dispelling.
All right.
That far to these.
Hello and welcome, everyone, to Ether Cosmology Research and Reading Night. Tonight we're going to be reviewing a physics textbook from 1911 from William Watson. And the specific section we're going to cover is Chapter 5, The History of the Speed of Light. To give an introduction, he talks about the observation with Romer using the eclipse timings and the re-emergence timing of Jupiter's moon Io to calculate the speed of light, and it comes out to roughly be, what the current accepted value is, and then from there they go on from where it was calculated, from this astronomical observation to where they started to get laboratory measurements confirming the speed here. So this is what we're primarily concerned with. So we're going to start with section 366 here. So Fizeau's method of measuring the velocity of light. The accuracy of the determination of the velocity of light by Romer's method is limited by the accuracy with which we know the diameter of Earth's orbit. Hence, it is important to determine the velocity of light between the two terrestrial points, the distance between which can accurately be measured. The first to perform this experiment was Fizeau. In 1849, measured the velocity of light by using a method depending on the eclipse of a source of light by teeth of a rapidly rotating wheel, the principle of the experiment resembling Romer's method. So maybe at the end here, we'll watch a little modern recreation of this method that Fizeau did for the first iteration of measuring the speed of light. A bright source of light was placed at L, figure 343, and after passing through a lens A certain portion of the ray was reflected from the surface of an unsilvered plate of glass G, placed at an angle of 45 degrees. The reflected ray came to a focus at F, this point being the principal focus of the second lens B. Thus, the light left B in a parallel beam, which after traversing the distance of about 4 miles, fell on lens C and was brought to a focus at the surface of a spherical mirror D. The curvature of the mirror is such that the lens C is at the center of its curvature, and hence the ray is reflected back along the path, so that on emerging from the lens C again, they form a parallel beam. This reflected beam then falls to lens B, which is brought to a focus at F and then falls on the plate glass G, where some of the ray will be reflected and some of it will be transmitted to the eyepiece at E, so that a bright star will be seen from an observer formed by the light traveled from D and back. All right, and here we go. Here's the side view of what that whole configuration looks like for the beam hitting or entering and then reflecting back, and then hitting the eyepiece, or either getting deflected or either getting reflected away. So the star will be seen by the observer, formed by the light which has traveled to D and back. The A toothed wheel at H, which can be rapidly rotated around an axle I, is also arranged so that the tooth passes F. So that when the tooth passes F, the light is intercepted, but the space passes F, and the light is allowed to pass. All right, if the wheel is slowly rotated, the observer at E will see a bright star when the space passes F, while when a tooth passes, there will be a darkness so that the wheel will be rotated to the star, alternatively appears and then disappears. But if the speed were such that it were more than 20 teeth per second, owing to the persistence of vision, a permanent star would be seen. If light took no time to travel from F to D and back at all, then the light that passed through the space would be able to pass back through again at the same space, since by supposition, the light takes no time to travel from F to D and back, and hence the wheel would not have moved between the starting time and the arrival back at F. However, if the light takes an appreciable time to travel, then the speed of the wheel is gradually increased. Then as it's gradually increased, it will eventually rotate so fast at the time of the return of light reaches F, and the wheel will have turned so that the tooth will have moved around and will occupy the part of the space which was occupied by a space when light started, so that the part of the return light will be cut off by the tooth, and hence the star seen at F will decrease in brightness. And as the speed is further increased, more and more, the light will be intercepted by the succeeding tooth, and finally the light gets through a space, is on its return intercepted by the succeeding tooth, and no star is seen. If the speed is yet further increased, the returning light will begin to get through the space after the one through which it passed on its way out, and the bright star will again increase. Hence the speed is increased, and the star alternatively appears and vanishes. If the wheel contains D teeth, then the angle from A to C to B, subtended by the interval of two consecutive teeth or space at the center of 360 degrees divided by D, or 2 pi over D in a circular measure, hence half of this angle, or pi over D, the angle through which the wheel has to turn, so that the tooth may exactly occupy the position occupied by the space, or occupy the position previously occupied by a space. If the wheel makes n revolutions per second when the first eclipse occurs, then the angle swept out by the radius from A to C in 1 second will be 2 pi n. Hence the time taken to turn through the angle will be pi over D, pi over D over 2 pi times n, or I over 1dn. Or I'm sorry, 2dn, sorry. If L is the distance between F and D, then the distance passed by the light of the wheel will be turned through an angle at pi over D is 2L. Hence the light will travel the distance 2L in the time of I over 2dn, or the light velocity is given by the formula here, where V is equal to 2 times the length over I times 2dn, which is equal to 4 times the length times the distance times the the revolutions times the revolutions. All right. In one of the experiments, L was equal to 8,633 meters, and the wheel had 720 teeth when the star was first eclipsed. It made 12.6 revolutions per second, so that it works out where V is equal to the formula given here, which comes out to be, what was it? 313 million meters per second, roughly. And more experiments of this were made by Cornu using this method. It gave 3,400,000 kilometers a second, or 186 million miles per second for the velocity of light. So does anyone want to popcorn for the next section?
Yeah, I could take you on if you like.
Alrighty.
Sure. Foucault's method of measuring the velocity of light. In the year 1850, Foucault succeeded in measuring the time light took to travel over a distance of about 20 meters. His method consists in causing a beam of sunlight to fall on a slit, as fig in Fig 345. I guess that's coming up there a ways down the page. Yeah, by means of a heliostat. Light transmitted by S passes through an unsilvered glass plate G, falls on a convex lens A, and then on a plane mirror B, which can be rapidly rotated around an axis perpendicular to the plane of the figure. For one position of the mirror B, the reflected light falls upon a second mirror C. This latter is a concave mirror, the radius of curvature being able to line BC. Hence, just ignore my cat in the background. She's pretending to be hungry after she's already eaten a ton. Anyways, the latter is a concave mirror, the radius of curvature being equal to BC. Hence, if the mirror B is at rest, the light reflected at C will retrace its path, being partly reflected at G, so as to form an image of the slit S at D, this image being observed through an eyepiece E. If the mirror B is rotated, the light is only reflected back from C once in each revolution if the mirror is only silvered on one side. If further, during the time taken for the light to travel from B to C and back to B, the mirror has appreciably turned. The return rays will be reflected by B in a slightly different direction to that which they would have taken had the mirror been at rest, and the image D will be displaced to D prime. The amount of the displacement being read off on a scale placed at D. In order to count the speed of rotation of the mirror B, which was driven by a small steam turbine, Foucault placed a toothed wheel so that the teeth were illuminated by the intermittent beam of light reflected from the rotating mirror. If the wheel was rotating at such a speed that during the interval between the two flashes, one tooth had just moved into the position occupied at the previous flash by the preceding tooth, then the wheel would appear to be at rest. And this is, we're actually talking about the strobing effect here. This is something that's used in strobe tuners, for example. And they used to sell turntables, that you play your records on, with a pulse-timed LED shooting at the side of the platter as it's spinning. And on the side of the platter, they used to have spaced rectangles, binary, if you will, black and white rectangles, across which that if you spun it at the right speed, like 33 RPM, the strobe would actually show one of, say, 4 of these series of rectangles going across the platter there as stationary, that you're timed and in sync with it. And it would look like the platter on one level isn't even moving. And it's the same kind of thing here. We're talking about strobe timing. So when this is the case, time taken by the mirror to make one revolution is equal to time taken the wheel turned to angle ACB. That is 1 over dn, where d is the number of teeth in the wheel, n is the number of revolutions it takes in a second. Hence, the number big N of revolutions is made by the mirror in 1 second is dn. In order to calculate the velocity of light, we require to determine through what angle the mirror B must turn to shift the image formed at the eyepiece from D to D prime. Since an image of the slit S is produced at C, we may, if we please, look upon the problem as to determine through what angle A must be turned so that the image of C formed by the mirror and lens A may shift from D to D prime. Let the two positions of the mirror B be indicated by the full and dotted lines in this figure 345. Then for each position of the mirror B, there will be an image of C formed in B. Let D and D prime be these images, as small d prime, as opposed to big D before. Then, as shown in figure 334, D and D prime lie on the circumference of a circle having its center on the axis about which the mirror turns and passes through C. Further, the arc intercepted between D and D prime subtends an angle to A at the center of this circle. However, if the distance from B to C is called L, we have the distance D to D prime as 2AL. Now, as far as the lens A is concerned, instead of taking C as the object as considering the two positions of the mirror, we may suppose the mirror B removed and take the two images D and D prime as the objects. And then you're splitting D, D prime over D, D prime. And that is the same as dA over average, the line segments AG and GD. Using the letters A, B, C to represent the distances, D, D prime, B, A, AG, to GD respectively, we have this cool formula here. Since the mirror makes big N rotations per second, the time it takes to turn through an angle alpha is alpha over 2 pi big N. And in this time, the light has traveled from B to C and back. That is a distance of 2L. Hence, the velocity big V of light is given by this big old formula here, 4 pi NL over A, which was essentially equal to 8 pi NL squared C over A onto L plus B degrees, alpha being degrees. Using this method, Michelson has obtained 299,853 kilometers per second as velocity of light with a possible error of 60 kilometers per second. Okay. Oh, it's possible he might have made a little teeny error. But we're damn sure that's exactly what that number is. That's why we put a 3 on the end. I'm surprised they didn't include the millimeters. But anyways, are we reading aberration too?
Yeah.
Okay, let's do that. A calculation of velocity of light was made in 1727 by Bradley from the apparent changes which took place in the observed positions of the fixed stars. The simplest method of explaining this principle of this method is calculating the velocity of light is to consider an analogous case. Suppose that a shot is fired from a cannon C, oh, they love that shit, big 346 to the right here, against a ship AB, which is moving rapidly at right angles to the direction of the trajectory of the shot. And if the shot enters the ship at point D, it will not leave the ship at point E. For while the shot is traveling across the ship, this latter will have moved forward so that some such point F will now be in the line CD of the trajectory, and hence the shot will leave the ship at point F. Now, as far as the track of the shot left in the ship is concerned, it appears to have come from the point C prime. Or the cannon is apparently displaced in the direction in which the ship is traveling. Now consider the ship to be replaced by the Earth moving in its orbit around the Sun, and the shot to be replaced by a light wave reaching the Earth from a star, the line joining the Earth and star being at right angles to the direction of the motion of Earth. If the Earth were at rest and a telescope, D, and this is Fig 347 over there now, telescope D were pointed at the star, the axis of the telescope prolonged would pass through star C, as in vertical. When the Earth is moving, however, the telescope is appreciably moved forward in the Earth's orbit in the time that elapses between the light waves reaching the objective D and the eyepiece. And hence, if the axis of the telescope is still directed so as to pass through the star, the waves of light will be left behind and form an image of the star at F to one side of the crosswires. Just as in the case of the boat, the shot, which if the boat were at rest would have reached the point E, hits the point F. Thus, in order to bring the image of the star on to the crosswires, the axis of the telescope must be pointed along FC prime. Now, in the time the light is taken to travel from D to F, the Earth has moved through the distance FE. Hence, the angle CDC prime, which is called the aberration constant, is alpha. And big V and little v are velocity of light in Earth, respectively, and have Earth over big V tan alpha, or V was V over tan alpha. Hence, if little v and alpha are known, V, that is the velocity of light, can be calculated. Now, did we catch that? That we're figuring out from the, quote, velocity of Earth, what the velocity of light is. See how they slip that right in there. Hence, okay, above explanation of the phenomenon as an aberration is commonly accepted. Yes, as we can see, because it's in this textbook in 1911. It is, however, by no means satisfactory, and I would concur. Thus, the quantity big V is the velocity of light in the medium filling the telescope tube, so that if the tube is filled with water in which the velocity of light is less than air, we should expect the aberration constant alpha to increase. No such effect is, however, observed. The discussion of the various theories which have been propounded to explain this discrepancy would lead us beyond the scope of this book, and so we must content ourselves with having drawn attention to the existence of the difficulty. As in, you guys got to figure it out. This is where our benefit of paying money to buy this textbook ends. Right here. We're not telling you nothing after this. You got to go find it out for yourselves. Are we doing the next one?
Yeah, I was going to, let's see, cover the emission theory and like why it failed, and then wrap up on the end here. It was like 2 more pages, so I'll finish this out.
Yeah, go for it.
All right. So the theories of the nature of light. So we've, read the beginning of Michelson-Morley a bunch, where he talks about the emission theory and the undulatory theory. Well, this is how they falsified one of the theories and showed that it was more likely that the undulatory theory was correct, and why they knew, based off of the prediction of angles of light in water versus a rotating mirror and the angle deviation that it produces. Like, they knew exactly how it would behave under these conditions. If the accepted explanation of aberration was Earth's velocity to derive this angle, like Stone was pointing out, then you would, you need that velocity component somewhere. So they're going to assert it's the Earth. So this would be how you would determine whether or not that's true. So we'll read about the previous theory here. So 369 here. Theories of the nature of light. We have hitherto assumed that the light consists of a wave motion of some kind, and now we have to consider the evidence on which that assumption is founded. There have been 2 principal theories of light, and one of these, which was adopted by Newton, is called the emission theory. A luminous body is supposed to be emitting small particles called light corpuscles, which travel out in all directions in straight paths and have the same velocity. These light corpuscles were supposed to cause the sensation of light by their impact on the retina. Since light can traverse not only empty space, but it comes in some form of matter, these corpuscles must be able to travel through space so that and also through matter, which they are supposed to do by passing between the molecules. So on this theory, the rectilinear propagation of light and the formation of shadows at once followed. In order to explain the law of refraction, the emission theory, it was assumed that a corpuscle came near the surface of separation between the 2 media and was attracted by the denser media. Okay. So thus, let AB in figure 348 represent the line of what is this demarcation between the 2 media of air and water. Oh, okay, gotcha. All right, and tend the path for the incident of the corpuscle. If v1 is the velocity in which the corpuscle travels in air, then we must resolve this velocity into 2 components. In the direction parallel to the surface of the separation of the media, and the other in the direction perpendicular to this surface, noted by, what is that, 1n and then 1m. If the water...
He's gonna use this word a lot. Hey, Alan, I just wanted to set it straight now. It's more like the word muscle, corpuscle. He uses that word a lot. I figured we'd call it straight now.
Oh, thank you.
Yeah, let's go with that.
Thank you. Corpuscle. Okay. All right. If the water particles exert an attraction on the light corpuscle, when it gets near the surface of separation, then the force must act normally on the surface, i.e. along ON prime. Hence, in the vertical component of the velocity corpuscle is increased in the horizontal velocity component in the direction of IN, which will remain unchanged. If we then take OM equal to OM and then ON prime equal to the increased vertical component to complete the parallelogram with the OR vector, will represent the velocity of the corpuscle in the water, and the path of the refracted ray will be along OR. From Snell's law, we have the following equation here. But since IO represents the velocity of the corpuscle in air, while RO represents the one in water, hence the ratio of velocity in air over velocity in water over the velocity in air. It's given by alpha mu omega. And since the refractive index of air to water is greater than unity, it follows accordingly that the emission theory, according to the emission theory, the velocity of light must be greater in water than in air. In the second theory, called the undulatory theory, the wave theory of light, the luminous body is supposed to set up vibrations in an all-pervading ether, and these vibrations are supposed to travel through the ether. When they enter the eye, they excite the sense of vision. During the passage of light from the source to the eye, the energy emitted by the source, in which we recognize when it is given up to the retina as light, must be stored up in the ether. On the older undulatory theory, it was supposed that light waves consisted of transverse vibratory movement of the ether itself, but the difficulty was introduced by the fact that if we suppose that the motion is propagated by the successive parts of ether, setting each other in motion by mutually attracting forces, these forces would be inclined to be in the direction in which the wave was traveling, and hence they would have a component in the direction of the wave normal, and this component would tend to set up longitudinal waves in addition to the transverse waves, which are required to explain optical phenomena. We have no evidence, however, of the existence of such longitudinal waves in the ether. In the later form of the undulatory theory, called the electromagnetic theory of light, the supposition is made that the vibrations consist not in the change of the position of the ether particles, but in periodic alterations in the electric and magnetic conditions of the ether during the passage of light. This supposition does not lead to the same difficulty as the formation of the longitudinal waves, as does the older theory, and hence possesses a marked advantage. Since both forms of the theory suppose the existence of transverse vibrations set up in a medium and only differ as to the nature of the entity of the displacement which constitutes the vibration, and the explanations which we shall make in the succeeding sections, since they do not involve the nature of waves, will apply to either form of the theory. We shall also sometimes talk of the displacement of an ether particle during the vibrations, but this must also be taken as a short, convenient method in stating the displacement of the electric and magnetic condition of ether at a point under consideration. We will now pass on to consider what assumptions as to the relative velocity of air and water have been made on the undulatory theory to account for the refraction of light when it passes from air to water. Let AB, figure 349, be the line of separation between air and water. Let P and P prime represent the wavefront in air. Then if V alpha is the velocity of light in air, then the time taken from P prime to the wavefront to reach the second medium will be P prime O over V alpha. During this time, the point P on the wavefront will have traveled into the water P, and if V omega it's VW. If VW is the velocity in water, it will have traveled the distance P prime times O over V alpha times V water. And if the center P is the radius equal to this distance, we describe the circle and then from O draw a tangent. OR, and then OR will represent the wavefront and the water at the instance when the point P prime on the wavefront P prime or double P prime reaches O. If ON and P and prime are the normals to AB, we have the equation alpha mu water is equal to the sine of NOP prime over the sine of N prime PR. Now the triangle double P prime O at P prime is at a right angle. Hence the two angles P prime PO and P prime OP are together equal to the right triangle. But the angles P prime ON and P prime OP are also together equal in right to a right triangle. Hence, the angle P prime ON is equal to the angle P prime P, or P prime PO. Ooh, there's a lot of P's and primes. In the same way that the angle N prime PR is equal to the angle POR, so that the equation given here, which I will not read aloud, is equal to this smaller reduced formalization of the same thing, where the velocity of light in air is to that in water the ratio of the refractive index of the air to water. So thus, as seen to according to the undulatory theory of light, travels more slowly in water than in air, while according to emission theory, light would travel more quickly. Thus, the measurement of the velocity of light in air and water would form a crucial experiment to test the validity of the rival theories. This crucial experiment was performed by Foucault, who placed a tube filled with water enclosed by glass ends between the fixed mirror of C in figure 345 and the rotating mirror B, and thus was able to measure the velocity of light and found it to be less than in air. This experiment, although it does not in any way prove the truth of the undulatory theory, yet shows that the emission theory at any rate cannot be true. What a wonderful ending with a classic hypothesis, null hypothesis, right? It's like the undulatory theory could be false, but we know for sure that the emission theory is wrong. So that's dope. So yeah, that was a history on the full context of this experimentally. So they knew all these values, which theory was making the correct predictions, and what it would and how light would have to behave to satisfy the conditions that were asserted by aberration in the old telescope here.
Hey, what was the date of this paper?
This textbook came out in 1911.
1911.
Yes, sir.
Okay.
Yep. Awesome. All right. Well, that concludes research and reading night. We will return next week with a new paper and subject. Let's see. Tomorrow night we have Twitter community night at 8. So we'll join the lads on Twitter, see what they're up to, touch base with everyone, disseminate new information, etc. Bring your globularist friends. Yep. BYO Globe or whatever. All right. Thank you, lads. Check in on the YouTube here. All right.